Hello and welcome to another episode of Invalid Entry. My name is James Taylor and today we are going to be talking about statistics and probability and some weird effects of how games generate worlds and all kinds of cool funky things. It is a Minecraft related video, but there won't be very much Minecraft actually in it. It's more about probability and statistics and human perception of it. In particular, we are going diamond hunting. This follows on from the last video. A couple of people, 3 or 4 people have been pestering me about this, saying, hey, let's talk about this trick you can do to find diamonds, and what did I think of it? The first person was actually someone who was cheating on the server, who came back and said, hey, if I use this, will I get banned? And like, well, no, you won't, because it's not a thing. And secondly, even if it was a thing, it wouldn't actually affect your statistics that much. And I will demonstrate why. This is backed up with a lot of work. I have put a lot of time and effort into this, and my computer's been running very hard to do some of the analysis that we can then use. So this isn't just me saying, in my opinion, it's wrong. This is me saying, I have looked and it is not true. And I will go into that. And a little bit about the code and how I did the math, so people can. If you're doing science, you would do it for peer review. I'll also try and publish my stuff onto my blog. I'll put a link down below. That might take me a couple of days to actually get up because I want to get good quality stuff. So in science, we call it peer review. Someone can come along and look at my results, and I really challenge someone who doesn't believe me to go away and do this themselves and do the analysis and actually find me proof and evidence. And I do mean proof. I don't just mean a 10-second video saying, look, it works here. I mean, I want to see 65,000 instances of this, and I will demonstrate that now. Okay, so diamond hunting. First of all, some caveats. This is done in Minecraft 1.17. I've also used the statistics from the Empirecraft world. So people are going to say, oh, there, you only did it in an amplified world. And the answer is, yeah, I don't actually think the probability will be that much different in other worlds, but people are telling me it works in the Empirecraft world, and therefore my statistics are relevant. Also, before anyone goes, oh, but people have already mined diamonds, I took a copy of the completely blank world before any blocks were broken. So I have a completely, what we call the virgin world, from the seed, completely generated. I did the analysis on. Secondly, this only works up to 1.17. People are saying it works to 1.16, 1.17. 1.17 does change how chunks are made because it actually is changing the Caves of Mine expansion. There's things in the caves which weren't there before. And 1.18 is going to radically change this. 1.18 is radically changing how diamonds are put in because the chunks are bigger. They actually go further down than they did before. So 1.18 is the second part of Caves and expansion. So this is valid for now up to 1.18 comes out. I'm really excited about 1.18, but this is 1.17. We're going to ask some questions of, fundamentally, what are the odds of finding diamonds? This is what it comes down to. This is what it all comes down to. If you find just one diamond, if you mine just one chunk and find one diamond, your stats are irrelevant. We're talking about someone who mines for half an hour through a bunch of chunks. What are the probability they find diamonds? Where's the best place to look for diamonds? Can you do the Lapis trick? Is it a thing? And also theory versus empirical. So before we get too deep into this, there are 2 types of probability. And what you do with those probabilities is the same, but how you generate the raw probability is different. So the first one that people are generally familiar with is theoretical probability, but there's also a thing called empirical probability. So theoretical probability is you looking at how you model the system that you're building, or if it's a computer game, you actually look at the code and go, well, this is the probability of a thing happening. So a theoretical probability, if you roll a dice, we look at a dice and go, well, it has 6 sides. So you have a 1 in 6 chance of rolling any of the numbers, like a 1 in 6 chance of rolling 6. So that's a theoretical probability. An empirical probability is where you don't look at the model, you just go and measure it. So I roll the dice 100 times, how many 6s did I get? And actually sometimes empirical probability is better than theoretical probability. Theoretical probability should tell you, well, I don't need to roll it. There's no randoms involved. I just get those values out. So theoretical probability should be better. However, we're talking about the real world. So the dice, the fact that you milled numbers or dots into the dice changes the weight of the dice, and therefore it affects the rolls. So empirical probability takes all those unknowns into account of real world situations. it's called Empirical. It has nothing to do with Empirecraft. That is what it is. So, and actually, quite amusingly, one of the guys, Stitch, who was saying, "Oh, give me the data. I have nothing but an empiricist." So, yeah, because this is a true empirical data. So we're going to take the empirical data, then apply that to our model later. So the empirical data basically means I need to take a copy of the world, look at every single block, and I could do that by literally taking a copy and going in and mining every single block. But that's a bit slow, and I've got computers. So I could mine bots to do it, but that's, again, not really what I want to do. I can just look at the data file that the game creates. So the game creates these world files when you load the world in. My first thought was loading the world in and flying around, loading all the chunks. That took too long. But there's actually a mod you can use to say preload chunks, which is really powerful. So I loaded all the chunks. I actually loaded way too many. I loaded minus 500 chunks to 500 chunks by minus 500 to 500 chunks. A massive area of chunks. I did only look at the 256 by 256 box that our Empirecraft world is world bounded bordered to. Loving the world border means my visualizations actually work because I haven't got something like 10,000 blocks at the one way. It's really, really nice world border. Anyway, take a copy of the world, analyze the world. I'll show you some of the code for that and what it comes out as. Before we go into it, let's talk about how the game works. The game basically breaks it down to chunks. It's a very, very clever technique that game designers use to stop you having to load in the entire universe at once. Keeps the game runnable on slower, smaller computers. Other games do similar tricks. You sometimes see levels, like you talk about in the game, talk about levels when you're loading a level in. Sometimes there's like a corridor. When you go through the corridor, that is the level loading, so the gameplay doesn't feel they're moving between levels. The game is quite clever in that as you walk to the world, you're unloading chunks behind you and you're loading chunks in front of you, so you sort of have this seamless progression of the world. As long as the server isn't overloaded, you can move along and you feel like an infinite world. Things like Eve work by systems, so each system is actually a different collection of server processes, and then actually when you go to an area, it's a grid, and that grid is a server process. So actually you don't have the entire solar system loaded at once, you only have the grids which are of interest. And it means it lowers the weight of processing on the server. If there are two people on the same grid, you need to worry about those two people communicating in terms of packets going back and forth, where their ships are going. Minecraft use chunks, so if you're on a chunk, you're on a particular server threads, and it works. It also means you can save chunks out and you can store the chunks nicely. So chunks are stored into region files to keep the number of files down. So we're talking about, and each region file is a couple of megabytes, but it adds up. It does add up. So I've got something like 2.5 gigabyte of region files that I had to be able to go into and analyze. There's a lot of data. Also, the number of blocks is quite impressive as well. So if you think that a chunk is 16 by 16, which means on one level of that, there's 256 blocks. Which basically means every 4 level there's 1,000, and that you can go from 0 up to 256. And in Amplified, you do have islands and things in the sky as well, so that's quite fun. Loads of caveats around how chunks work. So basically what happens is it generates the game generates all the levels, and then it inserts ores. It generates caves, it inserts ores. And in 1.17 and below, it puts 1 diamond vein per chunk. Or it tries to. So what's quite interesting here is it can fail. If where it puts it is air or lava or bedrock, then there's no ore. There's no diamonds in that chunk. What's interesting when I did the analysis is that actually a surprising number of chunks don't have diamonds in. I don't know if that's a symptom of amplified terrain, if the caves are bigger or not, but it certainly seems to be true that a surprising number of chunks don't have any diamonds in whatsoever. There's a difference here between theoretical and then empirical, because theoretical says, oh, what is the probability of you putting it in? Well, there's 1. How many diamonds are there going to be in a vein? There's a probability curve of that from a theoretical perspective. But then you start saying, what's the probability of it hitting a lava or hitting air or hitting something else that stops that vein being a big vein? So if you think about it, actually, when you are mining, if you're caving and you find diamonds, you're actually seeing half a vein. Half that vein is lost, so you're going to see less than the average number of diamonds, but you do find them faster because you're not mining yourself. So there's loads of caveats about how you find diamonds. Changes in 1.18. Similar rules are going to apply, like if it hits air, it's not going to spawn, but it does change. So instead of working out the probability of there being a cave or there being lava, what we can actually do is we can actually just empirically measure it and go, well, what is the probability distribution of there being diamonds in every single one? What's interesting is that once I know where 1 diamond a chunk is, I know it has to be a vein. And a vein means that it spawns the next diamond next to it. It's not going to be on the other side of the chunk. So if I have a diamond here in the chunk, I can ignore the rest of the chunk. I just look around it so there are any more diamonds in that pile. Then I move to the next chunk if I'm mining. So that if you know where one thing in the chunk is, it changes the probability of the rest of the chunk. And that's really important to realise. We're going to come back to that, but it's really important. If I have found a diamond, one diamond in the chunk, I see it, the probability that the block next to it is a diamond is much higher, but the probability that a block 5 blocks away is now 0. And that's really, really important to understand, because the inverse is true too. So we now have an understanding how Minecraft creates chunk by chunk. Important to it generates chunk by chunk. Let's look at why I'm doing this video and what the theory is. So the theory is that these people online, first of all, it's on TikTok, and obviously TikTok is a very reliable one. They say if you find diamonds, you now go 4 blocks north, always north, and you dig down and you will always find diamonds. Right? You may have to dig around a bit, which means it's not true. And that's how it is. Now, other people are then saying, no, sometimes you dig upwards. And they go, well, no, this is just bullshit. You're messing around probability. This is what we call goats behind doors. And I will find the reference to that in a moment, because I've said it a lot recently. So he basically goes 4 blocks north. Other person then says, hey, let's do it as well. Which one am I on? Yeah, basically this one. 116, 117, find Lapis, 4 blocks north, 4 blocks down, diamonds. Every time. And it's so frustrating when you see this, because it's like, well, there's no evidence of whether he put it there, there's no evidence of how many times he's done this or anything. Some people go, oh, we did it on stream and therefore it's true. It's like, well, he also seems to be being creative here, so there's really no evidence of that being true. And then you have blog posts like this saying, yep, 4 blocks north, 4 blocks south. The gold isn't always there, and obviously this is a picture they've made up, so obviously this is helpful, giving no evidence whatsoever. So we can basically just say what hell we like, no evidence to back it up, and therefore it becomes true. And other people like Stitch Online has gone, hey, I looked at this and I find it occasionally. It also matters about chunk borders. In the comments here, someone is saying the chunk borders matter. So if you're on like the second most north block, it loops round to the bottom of the chunk and counts forwards. And some people are saying it works 80% of the time, which means they aren't applying the chunk theory, because that's about right. Say about 10% of the time, 10-15% of the time, you go over the chunk boundary. Some people are. Some people are saying no. If you find Lapis, it will always be 4 blocks north, up and down. But what they're not saying, and what frustrates me, is they say, well, it's not always, because which Lapis block am I counting from, first of all, and then secondly, if I dig down to here, but they find diamonds here, not here, they say that counts. Well, there's a difference here. It's either 4, 5, or 6. So basically, when I'm digging down, if I dig this block out, I don't just see this block. I see this block, and this block. So I actually have 3 times the probability of seeing something than you actually realise. So when you dig a cave, you're not just digging the 2 blocks that you're mining. You're seeing the blocks on either side. You're seeing the block above. You're seeing the block below. So you're seeing more blocks than the block you dig. And I think that's half the problem, is that people don't understand how the probability works. Anyway, that's the theory. That's what we're about to disprove. Okay, and we're about to disprove it in big time. So what we do is we're able to use a thing called Quarry. Quarry is a Python library which allows you to... It actually is designed for you to make Minecraft servers in Python, which is quite a cool idea, because you could do things where the server's actually generating rules by different rules. Like you could do sand creeping, like deserts creeping across, that kind of stuff in Python. Really cool. Anyway, might break the game client, but you can do it. Anyway, so what I'm going to do here is I'm going to grab in... You have to bring in something called the Registry. So the Registry is basically an output from your jar file as to what the values are. So you have this file. Every byte in the file is basically a block, and it's got bytes on it. And you say, well, byte 24 means it's stone. That's actually coded into the jar file, so you have to have the correct version of the jar file for the registry file you're looking at, and we can basically do that. So I exported the jar file, get the right values, look at it, and when you actually upgrade your jar file to go to a new server that says upgrading the world, what you're actually doing is taking all your region files and recoding the region files to have the new byte value. So look at the old byte value, look at the new byte file, resave the region file. That's what's happening. So I have a region file, I open up the region file, I can grab a chunk out. The way the game works is you don't actually say go to block minus 7,000, 3,000. You basically have to go to the chunk and then say in the chunk I want to go to this block in the chunk. So all your block locations are actually done by offsets from the chunk border and which chunk you're in. It means you can actually, if you really want to, you could take a chunk and just flip chunks, which I think would be a really cool game mode. Towards the end of the season, I think it would be really cool if we just start saying, let's take this chunk and start restoring the world randomly. Let's put bytes back in, or let's take a chunk and just restore a chunk. Or get loads of different worlds and just start taking random chunks from random worlds and building a new world from it. I think that could be really chaotic. in some like a Doctor Strange type world going on. Anyway, grab all the bytes out, start analysing things, saying yes, this is layer 1, this layer 2, this layer 3, so on, all the way up. So you see bedrocks here. I've only done bedrock and ore here, so you see there's some first there's some redstone coming in. This dot here, this dot here, this dot here is the same vein, so you can see like slices through the layer. And then I started doing a bit more analysis and actually saying, hey, these are all the diamond veins in a region file. Can I analyze? So this is showing I can analyze it. I can pull out diamonds and redstone and coal and sort of show where they are for a particular level. This is, I think, all levels, 0 to 16. Just say if I found one in that dot, put a dot something. So we can now analyze with something called Quarry. Because I have the power of computers, I can just loop it. So I can say from this value to this value, just start looking at it. And you can start building more and more complex things. Because the world and people are telling me, oh, it changes what you're doing, I instead of writing the analysis and running the analysis twice, what I started to do was run a script and load it all into a database and then analyze the database, which is much faster than me going and looking at the world. Because open the world, you have to open files, find the coordinates, then find another coordinate and compare the two values. It's a bit slow. So loading all the ore into a database was much faster. My mistake was loading all the ore in, all the coal, all the redstone. But I wanted to because I wanted to provide other statistics, which I will show in a moment. The first thing I want people to remember, though, is people stuck at probability. This is a well-known fact. The human brain is designed to work as an animal. It allows us to do things like catch balls, allows us to throw things at moving targets. It allows us to drive cars and put our car through a gap safely every time. To do that, the way we analyse world speeds, probabilities, is we're looking for patterns all the time, and subconsciously we see patterns where they don't necessarily exist. It also means if I ask you to generate random numbers, you won't be able to do it properly. You can actually tell whether it's been done by a human or whether it's actually is a random number. For example, if I ask you to do a sequence of 1s and 0s randomly, let's say I want 100 bits, you won't put more than 3 or 4 zeros in a row, because you say it's very unlikely to have 5 or 6 zeros in a row or 5 or 6 1s in a row. The reality is, it happens a lot more often than people realise. So there's some counterintuitive things because people don't understand how probability works, or they intuitively don't understand probability. They might say, yeah, I worked out the maths, I can work it out, but intuitively it looks wrong. When you analyse it with maths, it comes out. So what we're going to do there is look at some of these probabilities. So what's really important is that humans suck at applying probability. That's what it comes down to. And in fact, humans are so bad at applying probability, there's an entire industry around this, which is gambling. You go to Vegas, the person who wins at Vegas is the casino. Continuously, the casinos exist because people suck at applying probability. They think they are the one. Reality is, if you're going to go gamble, expect to lose your money and do it for fun, and stop when it stops being fun. I cannot stress that enough, because the games are rigged. They're not rigged like, well, they probably are, but they're not rigged like the ball will always fall in the particular one they control. They're rigged in that the probability is in the casino's favour. Even if it doesn't seem that way, it always is. That's how it works. They spend millions hiring very, very, very clever mathematicians to make sure that, okay, it is that straightforward and that straightcut. Anyway, so what we have scripts which load this into database. The database looks like this. This is I use Django because I might use this later. So basically, I've got a jump model. I may put more than one world in later. Do not come up to me and say, "Hey, can you scan my world?" I'm not going to do it. Right? This took days of my. I'm only running them on Pis because I don't want to spend money on AWS machines for this. It's almost to spend money so I can do more analysis, sure, but I'm not going to spend a fortune on analysing Minecraft files for this. The server the world, it's on the block type, so I'm storing which kind of ore it is, I'm storing which region file it is, so I can then quickly go back to that region file and look at that region file again. I'm storing the chunk that I found the ore in. I'm storing the actual value, so this is going to be quite high numbers, like minus 7,423. The actual Y values can obviously 0 and 256, and then I'm storing the block in the chunk. So if it's in the chunk, I'm saying where it's 4 across and 5 down in that chunk. I'm doing it in the data model because it's not very expensive to store an extra 2 integers per row, but it means that I can then query without having to do maths inside the database query, so my query should be faster for some of the queries I want to do. So I'm storing one model, all the ore that we ever find. Then I have a management command, because it then does all my data for me. And my management command is going to basically connect up. It's going to load the registry. It's going to then run through each chunk, analyze the chunk completely from top to bottom, and save those into the database. So I end up with a model. I rewrote this slide to actually do it in stripes, so I could run 4 threads in parallel. Python is for all intents and purposes here, single-threaded. More efficient this way. I have 4 cores, so I can run 4 processes in parallel. Hits it very nicely. It would have been better, more efficient if I'd written this in Java, if I'm honest with you, and nicked the code out of the Minecraft jar file and done a whole bunch of other stuff. But I'm fast at writing Python, so the time taken for me to write the code versus the time to run it. It ran for basically 2.5 days on the Pi using a MySQL database, which is also on the Pi, on a different Pi, and now I'm suffering because the outcome of this is I have 17.3 million records in my database. That's every single all block in the chunks we've scanned. To give you some statistics, and by the way, people ask what tools I use a combination of Python and pandas. I use Django for a lot of my work, so I use Django. I use a thing called Tableau, which my license is about to expire actually, which allows me to do quick visualizations very quickly, so I take you through the Tableau stuff. I will publish all this information because I like peer review of my code, peer review of my data. And I also use pandas. That's the thing I mentioned, pandas. So Tableau. So it's 17.5 million rows of data. I also use Excel. So Excel is very important. It's got my raw figures in Excel. That is the equivalent of looking at 1,300 million. So 1.3 billion blocks is what I looked at in the Empirecraft world. 117 amplified world. So the first thing that we can graph, which is of interest to everyone, is the ore per level. Okay, comes out like this. Because we're in Amplify, we actually get coal quite high up in the world because we have more steeper mountains and things. What's really interesting is that iron drops off very sharply. There is no iron over level 63. If you find iron over 63, I really want to know about it because someone can put it there. What's interesting is that gold and copper do go above levels 53, but there's a significant drop off. You might look at this graph here and go, this is a bit interesting here, that there's no real coal below level 15. And the reason for that is that actually deep slate coal, and the similar down here. So we've got a lot of lines on here because we have duplicate of rows. The other reason that there's not much coal is that it may be other blocks, like it's going to be lava or it could be bedrock. There's nothing at level 1, but level 2 is interesting. So what we can do very quickly in here is I can take coal and deep slate coal, and I can actually merge those together like this. And when I do that, it will make this line straight. Now that's going to take a few seconds to run because it's going to re-query the database, and the database isn't the fastest thing in the world. But by using something like Tableau, I can create these visualizations and click on them very rapidly without having to write pandas and matplotlib and all the rest of it. So this is kind of funky. It lets us see what we expect to see these curves. I'm only interested in diamond and lapis, so I will just basically go straight to that graph. The diamond and lapis graph basically shows you here that my thing is updating. Here we go. That the diamonds show up between 0 and 15. We were thinking that you should mine at level 5, and actually that's not great, because if you mine at level 5, you're more likely to see the bedrock at level 4, and level 4 has a lower, therefore, probability of having diamonds. You're better off at mining at level 6, so you still see level 5 underneath you, but you see level 6, 7 and 8, because you're going to mine 6 and 7, you're going to see 8. If you really want to, you should mine 6, 7 and 8 and see 9, and that will give you the most probability of seeing these blocks. If you mine at level 5, then you're only going to see this many diamonds. On the block below you, you're better off mining 1 up at 6. Straight off, that's a freebie to everybody, that's what it is. The second thing that's really interesting is that the lapis here has a curve which is much higher. So the first thing that's interesting, and by the way, let's talk about why this might be real. Game designers have been known to make mistakes in code, like there are bugs in code definitely, but also random numbers are expensive, computationally expensive, and you want to generate a chunk as fast as possible because someone's gone into it, they want that chunk, right? So you've got to generate it and give it to the client as fast as possible. It's been well known that in certain games people reuse the random number. So if you generate a random number here, you reuse it over here. Or that the sequence, once generated, will repeat itself because computers are very expensive at making raw random numbers. We usually have a random number generator, a hardware random number generator on the chip, but it's really slow. So what you do is you use that once and then use pseudo random number generators after it, which are usually good enough. So there is a possibility that the two things are linked. The second thing is that we see here the peak of Lapis is about 4 blocks higher than the peak of diamonds. Okay, and the curves are beginning to nicely even out because I've taken so many records that this works out. So the probability of it being 4 blocks higher is actually a thing. So this is just a natural thing. The diamonds are naturally 4 blocks lower than Lapis. However, there's Lapis over here at 30, and there are no diamonds at 26, which are the 4 blocks or 5 blocks. There's no diamonds here. So people then start saying, no, it only counts for Lapis between here and here. It's like, okay, changing the goalposts because we feel like it. There's no reason for that. There's no reason for this to be true anyway. But say, oh, so it only applies here. Fine, we'll ignore these diamonds over here. Even though this just disproved the theory in one go, we're going to ignore it because reasons. Before we go into more reasons, though, so we've learnt one thing. We should be mining at level 5 or 7 to get a higher probability of getting diamonds. In fact, because this level 4 thing, you are better off mining slightly higher up. If Lapis was also true, by the way, you're still better mining slightly higher up because you've got more Lapis to find. Okay, and the other argument here, by the way, is saying if Lapis was always 4 blocks lower, then anything below level 4 can't be true because it would generate a negative diamond. So that's not true either. So there shouldn't be any Lapis below level 4. We've got, oh no, it's from the vein, like it could be the top of the vein rather than the bottom of the vein. So, well, make your mind. Do you have any idea how this thing works? No, we don't. We just saw something and we thought it was true because someone on TikTok said so. Okay, anyway. The second thing is that we should be, just so people are aware of how many diamonds we scan. This is all the chunks X, all the chunks Z. My program crashed every now and then here and here, but you see the number of chunks I've analysed in entirety are all these chunks. I've analysed about 67% of the entire chunks in our world. You can see a lot of chunks didn't have diamonds in, presumably because they're in caves or they're in lava or they're in bedrock. Therefore, there's no diamonds there. This isn't me going to look. This is the program looking at every single block and telling what the blocks are. Okay, so there are a lot of blocks there. Sorry, it's a bit grayed out. That one's a bit of a slow one to load. And the second thing that's interesting, I can also analyse where the diamonds are in a chunk. So you'd expect this to be a pretty uniform colour, like everything should be. If I find 256 diamonds, there should be 1 in every single cell. But it's not, because it's random, so there will be discrepancies over the entire thing. What's interesting is discrepancies can be quite high. So we've got a low of 472 and a high of 650 diamonds. So in every single chunk I analysed, I took all the diamonds I found and said where in the chunk were they found, and it comes out like this. There's no particular cell which never gets diamonds. There are these lower areas, see the lighter colours here. You could say, well, statistically on our, and if you ran this on a different world, you get a different pattern because it is just what the probability comes out with. This is what empirical probability tells us, is that, well, it just happens to be there's more diamonds here than there are over here. I would say if you mine north to south and find row 3, go for cell 3. That would be like my hint on our world, in our world border. That's where you're going to find the most diamonds. The reality is this isn't here how high or low they could be. They could be really diverse between the topmost possible diamond and the bottommost possible diamond, and it could be terrible. So I wouldn't use this as a metric to find diamonds myself. But it's interesting to know that we do not have a perfectly uniform layout. It is random. There are peaks and valleys. They're random because that's how random numbers work. It is not perfect. It is perfectly possible that we found all the diamonds in just one cell and the entire world. It's possible that world exists. It's very, very, very unlikely. There is also the mythical 40 diamond vein. The mythical 40 diamond vein is a 4 chunk vein. So the diamonds in one up to 117 can spawn up to 10 diamonds in one vein. You could have a blob of 10 diamonds in the top right corner. And in the next chunk above it, you could have 10 diamonds in the bottom right corner. The chunk to the right of that, bottom left, chunk below that, top right. So you could, in theory, have 10 diamonds in 4 chunks all touching each other, which means you could in theory have a 40 diamond chunk. And we have seen 12, 13, 14 diamond chunks where you've had 2 or 3 chunks on the border. You've had a 7 and a 7 making a 14 chunk. That happens. but there is the mythical 40 diamond naturally occurring chunk, and if someone finds that, we'll make a video just about that. So you can have these very large veins. If you look at where the chunk boundaries go, it's actually 2 veins touching. Yeah, happens. Okay. Whew, we're getting on a long way. We are 20-30 minutes into this video, and we're about to now hit the stats. So what I now have is a database of all of the veins, and in retrospect I shouldn't have included coal, but it does give you this very nice ore per level graph. As you see here, it's a very nice ore per level. I can merge these together slightly, and I will merge them together before I publish them, but there's a lot of data for it to manipulate in that. And it's only a little pie. The database is on a tiny little pie, because I wanted to turn my laptop off at night. Okay, so the first question we've got to ask ourselves is, what is the probability that we're actually looking for? So this is a mythical game here. So this is a Minecraft server of just one level. So we're going to pretend that there aren't verticals. We'll talk about how the verticals affect the probability of the flat world. If you mine through a world, at the moment, a 1 indicates the probability that there might be a diamond. Not that there is, that there might be a diamond. This is getting into quantum diamonds at this point. We don't know where the diamonds are, and they shift magically. Anyway, I start mining. So first of all, I dig this cell. And straight away what happens is, the probability of that being a diamond drops to 0. Because it's not a diamond, I mined it, right? The probability of everything else has gone up. And then, because I've dug that one, I can also see that cell. Oh, no. I can see that cell, and I can see that cell, and I can see that cell as well, because I can see into the blocks. So I can see the blocks. The probability that the diamonds are somewhere else goes up. So every time I dig a cell, I dig this one now, that one stays 0, that one becomes, oh, that one becomes a 0, so, no, where's my 0? There we go. As I dig my way through, the probability that the diamond is somewhere else keeps going up. Because it's not here, therefore it's probably somewhere else. Okay. We're going to show something which is counterintuitive now. I'm going to suddenly take a massive swerve and talk about pure maths. I think in the 60s was a game show, and you sort of went to the game show to get to the end, and at the end there were 3 doors. Behind one of the doors was the grand prize, behind 2 of the doors was a goat, or whatever, a booby prize, nothing basically. And the answer was, you picked a door. So what you did was you said, hey, I want that one. I'm going to use playing cards here, and you're looking for the ace, so I want that one. The game host would then take away one of the other 2 cards. One of the 2 cards which they knew was not the grand prize. So we don't know where the grand prize is, but the game host does. And they're going to take away one of the 2 cards. So they come along and says, oh, straight away, what are the odds that you've got the right card? Well, you've got a 1 in 3 chance that you've got 1 in 3 chance of winning the grand prize, right? So there's a 2/3 chance that you haven't won, and that's important. The game host says it's definitely not this one, flips the card over, opens the door, whatever. And then they ask you a question, do you want to swap? Do you want to go with the one you picked, or do you want to swap? This happens in a whole bunch of game shows, by the way. And it sort of matters whether you chose or not. And it does matter. So you imagine as when we phone the bank over the boxes. It's a little bit different in that situation, because you don't necessarily choose the box you have, but you see, and there's other probabilities in play here. Everything's a prize, it's not true or false, so the probabilities are a little bit different. Would you like to change your mind? And a lot of people argued for a long time whether you got an improved probability or whether you change your mind or not, because the question is which card. So the question is wrong. The question is which of these 2 are the ace. And you sit there going, it's 50-50. Like, it's either this one or it's the other one. It is that clear cut. Because if someone joined the game at that point and didn't know which one you selected, then the answer is 50-50. So if you don't have that knowledge that which one you selected in the beginning, the answer is 50-50. But that's not the question. The question is, what are the odds that your first choice was correct or not? So the reality here is, you've got a 33.3% chance, a 1/3 chance it's this one, but a 66% chance it's this one. And that's really counterintuitive, because you look at it and go, no, it's 50-50, there's 2 choices, it's one or the other. We don't know where it is, so it has to be 50-50. But it's not, it's 33-63, because we have that other knowledge. We've affected the probability of the cards. It's more obvious if I do more cards. When you do 3 cards, it's not that obvious. You have to do a lot of games to sort of show that there's a trend of always being better to select, because sometimes you'll lose. Okay, so let's have, I think this is all the red cards, all the black cards. I can't remember how I did this. I made this animation a while ago, or made this thing. So I'll have that card, please. That one's probably the ace, I think. We then reveal all but one of the card. What is the probability that you were right for the first time, or what is the probability that you were wrong first time? So we haven't shuffled these, we haven't swapped them over or anything. We've just said, you put your finger on that card and don't touch it. I'm going to display all the cards, show the aces and all these. So what is the probability here? And it's more obvious when you have more cards or more options that what is the probability you're right first time versus the probability you're wrong. It's a counterintuitive to begin with. When you look at it this way, the answer is it's the other card. It's like 25 times out of 26 you did not select the right card first time. That is fundamentally what the question is. The question is wrong. So what does it have to do with Minecraft? I recorded this in a different order than I thought it was going to. Right, so there's a lot of things, and it's definitely not the finish of that. Okay, so as you start mining away, the probability over here is increasing. When you're looking at a block of lapis, you're not looking at diamonds. So the probability that the diamonds are somewhere else goes up. And we've shown here very simply, as I begin to mine my way through a chunk, and I'm mining a one block tunnel, or a 2-high tunnel, but I can see the diamonds on either side as well, or the blocks inside. So I know they're not diamonds. So as I begin to mine through, and those are percentages on the right, so it's 0.4 that there's a diamond there. But it's creeping up and it's creeping up. It's now more than 10 times more likely than it was when we started mining the chunk. The second thing is you can ask what is the probability of, if I dig just one block out, if I dig this block out, I see this block, this block, this block, and this block. So if you actually look at the probability is actually almost 2%, 2.5%. If I dig one block, I see across the blocks, you see the probability go up. If there was one diamond, just one diamond, but there isn't one diamond, there's a vein of diamonds, and we know veins are on average 2.53 point something big, because it's only between 1 and 10, but there may be none at all. 1 and 10 diamonds, but it's weighted more towards the bottom level. So we can think in this little game that we've invented here, the diamonds are potentially a 2x2 grid, or they say the diamond vein is always going to be 2x2, there's 4 diamonds. The question is on the left here, how many different veins can a cell be in? So this block here can be, I'm imagining this game has boundaries, by the way. I'm imagining they don't go across borders, which is fine, right? So the vein could be this big, the vein could be this big, so there's 2 here, or it could be this big, or it could be this big, okay? So this block here could be in 4 different veins. It's only in 1 or none, because there's only 1 vein per chunk, but it's got a probability of 4. Now, you could argue, okay, well the vein could be this one, going from the bottom right up to the top left. It goes, no, that doesn't how the game works. Okay, we're always going to generate one side. If you did that, it just makes the numbers much higher, but the ratios are exactly the same. So if you did that for there, that would then be a 3 or 2 or something, and the ratios are still the same between numbers. You've just made all the numbers bigger. So we're going with these numbers. So these in the flat world is 4 veins. What you've got to realise that in the 3D world, you've got the height as well. So you've actually got, and you also you've got more than 2x2s, you've got 3x3s, and you've got other combinations that can happen. So the number of veins that a block could be in is incremented even more. So the effect of this is. So as I start mining here, I start taking out these numbers. Oh, no, that one should be a 2. So I'm having a little bit of lag because I'm recording at the same time. It's on my laptop. As I start taking out these blocks, these numbers go up much faster than the probability we're looking at, which is just a flat world of 1 diamond. So if I start mining down here to the same level, if I just take the same size, this is 0.439 on my previous world. Go to my veins, mine out the same sort of area. Already, my veins here are significantly higher probability of it being the diamond. And this is what it comes down to. So if I find lapis at this point, what happens is I start digging north. And let's just say north is this way because the probability. Once you dig, you've dug more out, and you said they're not either. your probability starts becoming significantly larger that there are going to be diamonds there. Not because there's a causality link, but because you've actually shown there aren't diamonds elsewhere. It comes back to what was the probability that you looked. I said diamonds are probably here. It wasn't, it was lapis. Therefore, the diamonds are somewhere else in the chunk. So the probability that they're north is higher than if you hadn't dug the chunk at all yet. That's what it comes down to. It's a perception thing, saying there's a causality there. There's not. That's just how it works. You've looked at things that it's not there, therefore it's somewhere else. So the probability of it being somewhere else is much higher. So the probability that if you have lapis A further up is higher, because that's how the probability occurs. We saw that in the distribution of the ore. And then for the probability, because I've found lapis, the probability of it being diamond is 0, so the probability of there being diamonds somewhere else is higher, because you've seen that there aren't diamonds there. That's how probability works. It's counterintuitive. But when I look at the diamond distribution, look at every single chunk, is there actually always diamonds 4 blocks north of lapis? No. We have analysed a lot of chunks, and I'm going to pause here and open up the correct spreadsheet or the correct statistics first and show you how they work. Oh, the first thing I can do, by the way, is I can find how many lapis there are, how many diamonds there are, and how many lapis there are. So I found 93,000 diamond ore blocks. That's not diamonds because you mine with fortune, whatever. Fine. I've also found 106,000 lapis blocks. So there is a relationship there that's about almost 1 to 1. It's about 0.8 to 1 to 0.9 to 1, something like that. What I can do is I can join the database on itself, and I can filter one to say where it's diamond ore or deep slate ore, because I'm not being called out on that. Say lapis or deep slate lapis, and say where the chunk. I have to limit my chunks I'm looking at, because otherwise the database falls over. And I find 122 instances where the diamonds line up, where we say, yes, there is definitely a diamond to the north of lapis. That isn't 122 veins, that's 122 ore. So if you've got 2 in a row, if you've got 2 lapis and you've got 2 diamonds, that would be 2. Right? Or if you've got 2 diamonds, one below each other, and 1 lapis, that would be 2 as well. So if you've got a vein, you should get a very high number here. Bearing in mind that this looked at 32 chunks wide by 256 chunks tall, I found 122 ore which lines up like that, where I should be finding, well, 256 in the first one, another 256, that's 500 in the second column, so every 4 should be 1,000. And I looked at 32, a size 32 chunks wide. So the stats here should be more like 16,000 veins. Multiply that by the ore, so that should be 2.5, should be in the region of 32,000, and the answer is 122. Oh, sorry, below the screen here. Sorry, scroll up a bit. 122. People then go, no, that doesn't count. That doesn't count because it wraps the block. Statistically, it does count, because the number of times that the lapis vein is more than 5 blocks south of the world border, and therefore it doesn't loop, is 10 out of 15 or 11 out of 15, depending on how you want to do the calculation. So the number of times this is true is more. And by the way, I've done it 4 blocks north, I've done it 5 blocks north. I'm not taking Y values into account, because people are like, oh, it only matters when the it's below here. The point is, statistically, that is not a high number. That is so low, in fact, that it lines up with the probability numbers we were generating here, saying what is the probability, in fact the raw probability, saying what is the probability that if I tunnel down, that a particular block has a vein in. Because the probability of a collision between the two is the same as the probability of the diamond just being north in the first place. So it looks like the probability matches the original probability of about 0.4. Okay? 0.4%, 0.4%. So if you find one, great, congratulations. And by the way, if you're mining and you say, I found lapis, like what can we do to stop people doing? Nothing, because it's just not true. If I find lapis and decide to mine north and mine down, great, go ahead. All you're doing is looking at more blocks. You are more likely to find diamonds. But that's just saying, if I find diorite or I find granite, oh, I found some granite, this isn't diamond, I'll mine north and look to see if the diamond's to the north. Fine, go ahead. Like that is exactly what you should be doing. If you don't find diamonds where you're looking, mine somewhere else. That's how you find diamonds. I find myself incredulous. I have to say, I find myself incredulous that I've had to do this. By the way, anyway, you can also then say, well, I only care about it in the block, so I can run the same query again here. Don't worry, my limit's 10 because my limit 10 applies to the count. I will run this query now, just to say I've already got that query in here for the same set of chunks. And what I will do is I will if this comes out in the thousands because of the chunk boundary right now, I will cry a little bit. Assuming there's no queries, I will publish this data. I will do the more complete data set. I will publish the results of what I found on my blog so people can go through the data, analyze it, and peer review it. I'm very keen on peer review. People say it's true, which doesn't happen on TikTok, by the way. No one on TikTok goes, oh, please go away and peer review my data, my research. Go away, actually do the peer. Don't come back to me saying, oh no, it does work. Like, if you're going to do that, find some data. Like do this sort of thing. Otherwise, I'm just going to ignore it because it's balls. And by the way, if you cheat and use this as your excuse for cheating, well, I'm still going to be in the suggestion of swinging the ban hammer. You see, these queries are quite slow because it's looking at an awful lot of data in the database, and the database isn't optimized. So I will cut and come back once I have that figure. The outcome of this is basically statistics work. If you look at chunk after chunk after chunk, if you find a one-off time of something happening, it's not enough. You have to look at more chunks, more probability. Don't be fooled by causality. Don't be fooled by, oh, if I find this, I find diamonds. The idea is that there's another one which is clay. I haven't analysed the clay. I don't think there's a lot of clay in our world, actually. If you find clay, you dig down, you'll find diamonds. It's like, yeah, if you find a chunk and dig down, you'll find diamonds. Anything which then ends with that, oh, you might have to dig around a bit. You might have to dig around a bit means you haven't got a clue where the diamonds are. There is no link between the two. That said, there are games out there where there is a causality link. We saw it in Wind Waker, the Link game, a Zelda game, where they had used a particular seed. So when you get to the level with the cannonballs blowing up water, it's like battleships level, the probability early on, if you saw something happen early on, it means that they're in a certain place, and it means the speedrunners can then optimize their run. So you do see mistakes in probability generation, you do see mistakes again. Mistakes in random number generators are actually a thing that is like a background nightmare to me, because I work in finance, I work in credit cards, and one of the things that we've seen in the past is that the Oyster system, which is made by Cubic, which is used on London Underground, it's used in some other places, originally used something called MyFair Classic. The MyFair Classic were by NXP, who are very clever people making chips, but they skimped on the random number generator. So on a MyFair Classic card, you could basically break into the cards. That was actually a hack, which was a lab attack. They actually took the chip apart with an electron microscope, saw how the electron numbers were generated, then reverse engineered it to being a script. They don't use MyFair Classic cards now, they use MyFair DesFire cards now, which have the same electronic interface and have the same APDU binary interface, but they have different circuitry inside the chips. They don't have the same random number generator. But a bad random number generator led to an entire group of products being completely wiped out, and confidence in the system as well. I would say there were people who were sitting there going, the MyFairs aren't very good. That brand name has recovered now because it is using the DesFire cards. You can't buy MyFair Classic cards. You can use MyFair Classic like on DesFire cards, but I don't believe you can buy the Classic cards anymore. So random number generation is a very big thing. It's a very difficult thing to do as a computer engineer, which is, computer engineers are all about repeatable things. So you can do it on, off, on, off. You run a program, it comes up the same number every time. So random numbers are not something that are very natural. A lot of programmers don't understand random numbers either. A lot of programmers don't even understand how to test their random number generator when they build one. That is a subject in its own right. So random numbers are difficult. There's some very cool things people do to generate random numbers involving things like lava lamps. I've seen some mechanical dice rollers to generate the seed for random numbers, some hard random numbers. A lot of them use electrostatic or static discharges, which again is good, but then your machine can die over time because your capacitors can actually wear out and give you less randomness. There's also some very interesting mathematicians. Alan Turing actually did work on how to turn a not perfectly biased list of ones and noughts into a perfectly averaged out random series of ones and noughts. So there are some very interesting number of random numbers. So people do find issues with random number generators where they are biased more towards one thing than another thing. In implementation, that is where empirical measurements are more powerful, because they're actually measuring if a thing is real or not, as opposed to, for example, the theoretical, where it doesn't take into account the realities or those other things. So yeah, this is where we are. We're basically disproving this. I will update this at the end when this query has come back, but it will come back with a number which is significantly lower than it should be. That isn't to say it doesn't happen, it is to say it doesn't happen enough to be a statistical link. I realise this is now 50 minutes, so I want to thank you very much if you got this far through the video. Please leave a comment down below if you got this far. Just say, hey, I made it to the end. If you want to go away and do more research, or you want to have more stats, I will put it on the blog. When I've done that, I'll update the link below to have the blog link. If it's not in there yet, I'm still collating the data and put it on there. If it turns out after all the data collation and publishing the data that I was wrong, I will remake this video. And I will do a public apology whilst, I don't know, I'd say eating my hat, but my hat isn't very tasty, so I probably won't. I like my hat. Either way, thank you very much. And I will see you all in the next episode, which may or may not be Minecraft, maybe something more interesting like Nerf guns. Right, ta-ra.